Welcome to AI Paper Slop. If you're an ML engineer or, an AI researcher treating large language models, you know the absolute pain of tuning learning rate
Oh,
schedule.
was the worst.
Right. So we're jumping straight into a paper today that wants to eliminate that entirely. It's called ScheduleFree plus Scaling Learning Rate Free and Schedule-Free Learning to Large Language Models by Aaron DeFazio from FAIR at Meta.
Yeah, and the stated goal here is zero fluff. No more of those YOLO training runs where you just guess your hyperparameters, launch the run, and pray.
Yeah, exactly.
DeFazio essentially wants to ditch traditional learning rate schedules completely. So things like cosine decay or warm-up stable decay, also known as WSD. He wants to replace them with a method that dynamically adjusts itself.
So for everyone listening, here are your key takeaways for the next 60 seconds. Schedule-Free Plus solves the scaling failures of previous schedule-free models using 4 core mathematical fixes. 1, reintroducing inner momentum to stop large batch divergence. 2, using an approximation of the Polyak step size to become completely learning rate free. 3, applying warm starting. And 4, increasing outer momentum.
And the headline result from doing all that is honestly striking. For long-duration training runs specifically, they look at the 1,000 tokens per parameter mark, schedule-free, plus outperform state-of-the-art schedules by 31%.
Whoa.
Yeah, it reaches the exact same loss in significantly less training time.
A 31% reduction in training time at massive scale. I mean, if you're provisioning thousands of GPU hours on an H100 cluster, that is a total paradigm shift for your budget.
Definitely. It's huge.
So today, we're dissecting exactly how Meta pulled this off under the hood. But before we get to the plus in the schedule-free plus commit, we probably need to establish the baseline, right?
Yeah, we do. So standard optimization involves setting a peak learning rate, decaying it over time, and just hoping the model converges perfectly right as you run out of tokens.
Which is a huge gamble.
Exactly. Schedule-free does something fundamentally different with the optimization sequences. So the original schedule-free learning paper from early 2024 completely replaces the traditional schedule with a really aggressive form of moving averages.
Okay, so break that down for us. What are we averaging?
To understand the baseline, we look at 3 specific sequences of variables. The optimizer tracks at every single step. They call these the Z sequence, the X sequence, and the Y sequence.
Okay.
Standard optimizers usually just track your model weights at each step, updating them based on the gradient. In this method, the Z sequence represents those standard step-by-step weight iterates.
But the optimizer doesn't just stop at Z, right?
Right. It builds the X sequence, which acts as a continuous online average of all those Z iterates over time. And then the third sequence, Y, is where the gradients are actually evaluated.
So Y is kind of a mix of the two.
Yeah, it's an interpolation. Mathematically, it's a blend that's heavily weighted toward that average sequence, X. But it pulls in a tiny fraction of the most recent information from the standard sequence Z.
How tiny are we talking?
Typically, the interpolation weight is set to around 0.9. That means the point where you calculate your next gradient is 90% based on the historical average and 10% based on the absolute latest step.
I always think about this visually, almost like exploring a physical mountain range in the dark.
Oh, I like that.
Right, so the Z sequence is like an erratic scout. The scout is out there running around the slopes, reacting to every local dip and bump, just, exploring the gradients.
Yeah.
The X sequence is the reliable map you're slowly drawing back at base camp based on everywhere the scout has been, so it averages out the noisy path. And the Y sequence is like a physical tether connecting them.
That's a really good way to put it.
It keeps the point where you evaluate the landscape firmly grounded to your reliable map while still letting the scout dictate a bit of the immediate direction.
Exactly. And the gradients for the next step are computed at that tethered point.
Oh.
But here's the crucial API change for anyone actually implementing this in PyTorch. The model you evaluate, the checkpoint you actually use for validation loss or final inference, is not the scout, and it's not the tether.
It's the map.
It's the map. You evaluate the X sequence, the average. The loss values for that average sequence are just significantly lower and more stable than the active training steps.
So the averaging is basically doing the exact same mathematical job as a decaying learning rate schedule.
Right. It produces beautifully smooth loss curves without forcing you to predetermine when the training run is going to end.
Okay, so if this averaging works so well, why did this original paper need a sequel? Where did it break?
Well, it hit a scaling cliff. The original method was tested on V100 GPUs with relatively small batches, But when they tried to scale it up on, say, 120 million parameter Llama 3 architecture, the original schedule-free hit a brick wall at about 2 million tokens per batch.
Oh, wow. So it just completely fell behind Atom W.
Yeah, Atom W hits a cliff at around 4 million, so falling off at 2 million is a problem.
So how did they fix it?
The fix was actually reintroducing inner loop momentum, specifically setting beta 1 to 0.9. DeFazio had initially removed it from Atom W to save memory because, it didn't really help on small models.
But at scale, it becomes vital.
Exactly. The paper also mentioned something called C refinement as an alternative fix, where you use a hyperparameter constant of like 50 or 200. But they proved that inner momentum actually gives a lower loss at those larger batch sizes.
I mean, that makes total sense if you think about scale. Like, steering a small speedboat, a small batch, is easy to correct instantly, but a massive cargo ship needs internal momentum to just maintain a stable trajectory through the waves.
That's exactly what's happening mathematically.
So inner momentum keeps the large batches stable initially, but when they ran these massive models for longer durations, I know a completely new issue broke the training, right? Something about weight decay.
Yeah, it was a pretty glaring anomaly. So standard practice for an optimizer like Atom W uses a weight decay of around 0.05. It just keeps the model weights from growing out of control.
Right.
But the original schedule-free method only performed well if you used an unusually tiny weight decay, like around 0.0002.
Wait, dropping from 0.05 to 0.002 is massive. If you don't decay the weights enough, don't they just explode?
They do. The paper notes, they saw weight norms growing to over 3,000 and sometimes even 5,000 on long training runs.
That's insane. Regular Atom W keeps those norms practically flat. Why use such a tiny weight decay to begin with? Letting weights hit 5,000 sounds like a one-way ticket to numerical instability.
Well, it was a messy workaround for a phenomenon called gradient norm drift.
Okay, what is that?
So as you train a neural network, especially as it begins to converge and find the floor of a loss basin, the landscape flattens out. Naturally, the gradient vectors become shorter. And in standard stochastic gradient descent, your step size is directly proportional to the size of the gradient.
Oh, I see. So as the gradient shrinks, your effective step size just shrinks along with it.
Right. The model starts slowing down organically just because the slopes are getting gentler.
So the tiny weight decay was basically a hack to counteract that slowdown.
Exactly. By barely decaying the weights, they allowed the overall weight norms of the model to grow massive.
Yeah.
And mathematically, larger weights inherently induce larger gradients in neural networks.
So by artificially inflating the weights, they forced the gradients to stay larger, which prevented the learning rate from dropping prematurely.
You got it. Use a complete Band-Aid to prop up the gradients.
But you obviously can't just let your weights explode to 5,000 in a massive language model. So how do they stabilize the gradient drift without blowing up the weights?
They turned to a concept called inverse gradient norm weighting. Honestly, I consider this the crown jewel of the whole paper.
Oh, really? Why?
Because instead of letting the weights explode to keep the gradients large, they stabilized the weights entirely by dynamically scaling the step size.
Yeah.
They literally just divide the step size by the L1 norm of the gradient.
Okay, let's logic that out. If the gradients are naturally getting smaller as the model trains, dividing your step size by that shrinking gradient norm counteracts the effect.
Right.
Because as the denominator shrinks, the multiplier grows. So it keeps the effective step size constant regardless of how flat the loss basin becomes.
Exactly.
But wait, if we divide by the gradient norm, what happens when the gradient approaches zero? Doesn't the step size approach infinity? Doesn't the whole model just explode?
Yes. And that is exactly why they cannot use raw, instantaneous gradients for the denominator.
Okay, so what do they do?
Well, this concept actually stems from the Polyak step size, which is a classical idea from deterministic optimization theory back in the 1980s. The Polyak step size inherently uses this inverse gradient weighting.
But nobody uses Polyak steps in deep learning today.
Because neural network gradients are stochastic. They're computed on small mini batches of data, which makes them incredibly noisy. If you divide your step size by a single, noisy, near-zero mini-batch gradient, the step size spikes to infinity and your training run collapses instantly.
Right, so to make Polyak viable in a noisy environment, you have to smooth it out somehow.
Exactly. They apply an exponential moving average, an EMA, with a coefficient of 0.9 to the stochastic estimates. So they keep a running, smooth tally of the gradient magnitudes.
Okay, that makes sense.
But estimating the denominator still poses a statistical problem. Classic Polyak divides by the squared gradient norm. And squaring a noisy stochastic estimate amplifies the noise exponentially.
Oh, right. So outliers become massive and just destabilize the whole moving average.
Right, so the math trick they use here is honestly brilliant. Instead of using the squared gradients directly, they swap to an L1 norm approximation.
The L1 norm, so just the sum of the absolute values of the gradients.
Exactly. The L1 norm is vastly more robust to outliers than the sum of squares. But to make the math align with the original L2-based Polyak theory, they rely on this really neat statistical property.
Wait on me.
Assuming the gradient noise is normally distributed, the expected value of the L1 norm multiplied by the square root of pi over 2 gives you a highly accurate approximation of the L2 norm.
Wait, really? The square root of pi over 2 is roughly, what, 1.27?
Yep, about 1.27.
So by taking the smoothed absolute sum of the gradients, multiplying it by 1.27, and dividing the step size by that result, they get an incredibly stable Polyak denominator.
It works perfectly. The moving average smooths out the variance, the L1 norm ignores the extreme outliers, and the scalar corrects the geometry. It completely eliminates the need for that tiny weight decay hack. The weights stay perfectly flat.
That is so elegant. Let me introduce a different analogy here.
Go for it.
Using a standard learning rate schedule is like driving a car where you have to pre-program exactly how hard you will press the gas pedal at every single minute of the trip before you even leave your driveway.
Yeah, that's a great way to think about WSD or cosine schedules.
Right. But the Polyak step size acts like a smart cruise control system. It constantly measures the steepness of the road, the smoothed L1 norm. When the road flattens out and the gradients shrink, the cruise control automatically presses the gas harder to maintain your speed.
And the absolute beauty of this cruise control is that it eliminates the learning rate hyperparameter entirely.
Which is massive. I mean, if you're an ML engineer, you spend immense amounts of compute just grid searching for the optimal peak learning rate for a new architecture.
Oh, easily.
And this paper proves that using the Polyak step size with the smoothed L1 approximation just calculates the optimal step size for you on the fly. It is both schedule-free and learning rate-free.
The algorithm effectively scales itself. The step size becomes invariant to the overall scale of the loss function.
Okay, so we've essentially assembled all the pieces of schedule-free plus stis. We added inner momentum to steer the large batch cargo ships. We implemented the Polyak step size with the L1 trick to drop the learning rate, dynamically adjust the steps, and fix the weight decay explosion.
Right. And the paper also includes some minor additions like warm starting the sequences and increasing the outer momentum to further smooth the trajectory.
The underlying math is just incredibly elegant, but let's look at how it performs in the wild, against the current heavyweights of language model training.
Sure. So Meta ran a series of scaling ladder experiments, training models up to 2 billion parameters on up to 500 billion tokens. And they benchmarked ScheduleFree Plus against the best schedules currently dominating the field.
Specifically, properly tuned linear decay schedules and warm-up stable decay, right?
Exactly.
Warm-up stable decay, or WSD, has been the absolute darling of the open-source LLM community lately because it provides such predictable performance. How did ScheduleFree Plus compare?
The results are highly dependent on the duration of the training run. The paper really highlights a specific metric, 1,000 tokens per parameter. So for a 1 billion parameter model, that means training on 1 trillion tokens.
Okay, so a very long duration scale.
Right. And at that scale, ScheduleFree Plus provides a 31% reduction in training time to reach the same loss as the state-of-the-art tuned schedules.
Let's just frame that for your daily workflow if you're listening. Cutting your compute cost by nearly a third on a massive pre-training run translates to millions of dollars in saved GPU time.
Oh, easily millions.
Or just getting your model out of the oven weeks earlier. But there's a catch for shorter runs, right?
Yeah, there's a caveat. The paper clearly states that for short-duration training, say 20 to 100 tokens per parameter, ScheduleFree Plus does not show a final loss advantage over a perfectly tuned WSD or linear decay schedule. It just ties them.
But even when it ties on loss, you retain a massive operational advantage, which is anytime stopping.
Oh, anytime stopping is huge.
Right, because with WSD or cosine, you have to know your total token budget in advance to initiate the decay phase at the right time.
Exactly. If you decide halfway through that you want to train for another 100 billion tokens, you can't easily extend a decaying schedule without causing a massive spike in loss.
But schedule-free means you just pull the plug whenever you run out of money or patience. And the model evaluated at the average sequence is just fully baked and ready for inference.
The operational flexibility is immense. And, the paper also dedicates time to demonstrating the empirical failures of cosine schedules.
Oh, really? Because for years, cosine decay was the gold standard in the literature.
Yeah, popularized heavily by early transformer papers. But DeFazio's experiments systematically show that cosine schedules consistently tie or underperform simple linear decay schedules when both are properly tuned.
So the mathematical optimization landscape is shifting away from cosine entirely.
It definitely seems that way.
Okay, so we have a method that scales to massive batches, entirely drops the learning rate hyperparameter, saves 31% compute on long runs, and grants anytime stopping flexibility.
It's a pretty good package.
It really is. To wrap this up, I want to step back from the benchmark tables. What is genuinely fascinating about this paper is how a cutting-edge LLM scaling technique reconnects the field with incredibly old, established theory.
Yeah, the final observation in the paper addresses a broader theoretical disconnect in modern AI. Schedule-free learning essentially provides a rigorous mathematical foundation for techniques that are incredibly hyped right now, specifically model merging and checkpoint averaging.
Model merging is literally everywhere right now. People take 5 different fine-tuned models, average their weights together in various ratios, and somehow produce a superior model.
And to a lot of practitioners, it just feels like an inexplicable hack.
But it's not a hack.
It is not a hack. The success of model merging and the success of schedule-free averaging is anchored in classical convex optimization theory from the 1980s and 90s.
So we're talking about techniques like stochastic weight averaging and Polyak-Ruppert averaging.
Exactly. They laid the groundwork for this decades ago. The deep learning community often treats LLM optimization as this entirely new, mysterious field where empirical vibes rule.
Just trial and error.
Right. But the specific shapes of the loss curves we see today, even the steep drop-offs produced by the decay phase of WSD schedules, are precisely predicted by classical convex optimization mathematics.
The map and the scout, it all returns to the power of the averaged sequence.
Yep. The literature drifted away from these theoretical underpinnings because the stochastic noise of neural networks broke the classical formulas.
But DeFazio's work pulls the field back.
It does. It proves that these classical methods, when adapted correctly with modern fixes like the smooth L1 norm and inner momentum, are actually the master key to scaling.
In a world obsessed with finding new hyper-complex optimization tricks, isn't it incredible that the ultimate solution to scaling large language models might just be classical convex optimization theory from the 1990s, updated for stochastic noise and applied to checkpoint averaging? Next time you see a new magic schedule pop up on your feed, ask yourself, are we just ignoring the math? Keep exploring the theories beneath the code, and we'll see you on the next breakdown of AI Paper Slop.